Hello, thank you for joining my presentation. I will be discussing a certain random walk in random environment, which is called the mod variable range hopping model, or the mod random walk. Specifically, I will be discussing a certain subdiffusive scaling regime. And this project is joint work with David Croydon and Ryoki Fukushima. This is the model, so it can be constructed in a two-step procedure. In the first step, you sample a random environment omega, which consists of the atoms of a one-dimensional Poisson process, meaning that the increments between the omega i's are going to be IID exponential, and the intensity rho is going to be the parameter of the model. Then, given omega, we introduce a continuous time random walk x, supported on omega, starting initially in omega 0, and having jumps occur always at rate 1. So it's a constant speed random walk. The probability of jumping from omega I to omega j is going to be proportional to this expression, which I'm denoting here with a C to indicate conductance. So more precisely, the probability of jumping from omega I to omega j is equal to this expression divided by the sum of all conductances going out of omega I. Down here there is a sample realization of this process. So you have the random point process down here, and then on the point process a random walk, which starts out in omega 0, then maybe has 3 nearest neighbor jumps, 1 jump over 2 sides, and maybe even 1 jump over 3 sides. So one feature of the model is that the jump length is unbounded, but looking at this expression for the conductance, we can already guess that long jumps are going to be quite rare. And another feature is that the process is reversible, which you see by looking at this expression and noting that it's symmetric in I and j. The question I want to answer about the process is about its long-term behavior, so specifically its long-term behavior under the annealed measure, which is the probability measure jointly of environment and random walk. And it's going to turn out that this answer depends on rho. So specifically, if rho is small, then we find large gaps in the point process, and because of the specific form for the conductance, the random walk has trouble jumping large gaps. So those large gaps are going to introduce a blocking mechanism, which means that for rho small, the random walk is going to be slowed down by the large gaps. Specifically, we have the following phase transition. The first part proved by Caputo and Fortunato, where they showed that for rho large, specifically rho larger than 1, the correct rescaling is diffusively. So looking at this rescaled random walk, you converge to Brownian motion at some deterministic positive variance, which of course depends on the parameter. So one interpretation is that up to this variance, the long-term behavior of the random walk is the same as for usual simple random walk. And we looked at the converse situation, so small rho smaller than 1, and we find that in this case you need to apply a subdiffusive scaling and obtain convergence to some limiting process Z, which we can describe explicitly, but it's not Brownian motion. Note that the exponent here is larger than 2, so this really is a subdiffusive rescaling, which is due to the asymptotic influence of the environment. So I want to quickly convince you that rho equal 1 is the critical parameter for this model. So for this intuition, I will be discussing a certain nearest neighbor version of the previous dynamics, where it's still a constant speed random walk, so jumps occur at rate 1, and the conductance are the same as before, but truncated so that in each step you only go either to the left or to the right. And one tool that is classical for reversible Markov chains is to look at what is called the effective resistance, which goes back to the analogy between reversible Markov chains and electrical networks. And we can compute this explicitly in the nearest neighbor case, because here the transition graph is just a tree. So looking at the effective resistance between the starting point and some far away site, the effective resistance is just the sum of the edge resistances in between, which are equal to 1 over the conductances. So you end up with this sum, where you quickly convince yourself that the summons are IID and have this tail behavior, and you observe that the intensity of the environment, rho, appears as the tail exponent here. And this is the explanation why rho equal 1 is critical, because of course for rho larger 1 you have a law of large number, so this sum here is going to grow linearly at some deterministic rate, whereas for rho smaller than 1 the summons don't have a first moment, so the correct rescaling is this stable rescaling, and moreover the multiplicative factor is going to be random, so S1 being a rho stable random variable. So in the rho smaller than 1 case, the effective resistance is much larger than in the rho larger 1 case, so the process is going to move much slower. So here are some key steps in our proof. The first step actually is similar to what I did in the previous slide, except you need to do it for the untruncated model, so not nearest neighbor. And it turns out that the same behavior occurs. So under this stable rescaling, the effective resistance converges to a rho stable subordinator. So in this case, of course, you cannot write down a closed form for the effective resistance, so you need to apply some approximation techniques. Then we study a certain auxiliary process, which is defined as the effective resistance between the process at time 0 and the process at some large time. One way of looking at this is that you apply a transformation that gives you a new space, which we call the resistance space, and this process is going to be almost a martingale in this resistance space. So more precisely, this process here is a martingale up to a corrector, which is going to be negligible under this stable rescaling here. And then we apply known results for the convergence of reversible Markov chains and prove that this auxiliary process is going to converge to time change Brownian motion. And I just highlight here that the time change we are going to compute explicitly, so you can write it down, but I'm not showing it for time reasons here. Okay, this is of course nice, but we are not really interested in the auxiliary process, but instead we care about the process in the argument here. So what we formally need to do is we need to invert this mapping here. Of course you need to say inverting in quotation marks, because there is no reason why this function should be 1 on 1. But in step 3 we show that this can be indeed justified rigorously, asymptotically at least, and the result is what you would expect. So the scaling limit for this process, which is the argument here, is the limiting process from step 2, and then you apply the inverse function of the process from step 1. So more precisely, the right continuous inverse of the stable subordinator. Let me finally show you some simulation to convince you that the result is true. So on the left hand side I'm showing the process in the original space, in the physical space, and I've drawn a line here for each omega, and it's a fairly long-term picture, so the omegas are quite dense. On the other hand side, this is the process in resistance space, where the gap between lines is proportional to the difference in effective resistance between those sites. And you see that asymptotically there are going to be large gaps which will persist. So the gaps here are going to correspond to the jumps of the stable subordinator that I had previously in step 1. The process in resistance space we have proved is time change Brownian motion, and indeed you can see, for example, in this part where the resistance space is fairly dense, that this maybe looks somewhat like Brownian motion. But then you have large gaps which are hard to cross for time change Brownian motion. So what happens is that the process has to spend some time on the left side of the gap before it has exactly one crossing, and then afterwards it's going to spend some time on the right side of the gap. So this leads to some interesting behavior in the physical space. So for the process we are interested in, the gap that you have in the resistance space is going to disappear. So it's asymptotically not visible, but its effect is still visible because you have first reflection from the left, corresponding to this weighting on the left hand side. Then there is the crossover, which is not visible, and afterwards you have a reflection from the right. So the large gaps are going to introduce a blocking mechanism which is going to lead to either reflection from the left or from the right, which is also visible, for example, in this part. So there's a medium-sized gap which the process did not succeed in crossing, which leads to reflection just from the right in this case. And finally, I note that the results that we applied to prove this are fairly robust, so we can allow for some generalizations, which I don't have time to explain, but I just mentioned that, for example, the nearest neighbor model I talked about before is also contained, and we find that in this case a similar scaling limit appears. So indeed the nearest neighbor restriction doesn't change the behavior of the model in a significant way. Thank you for listening.